All right, the voice said recording in progress, and I noticed it's 2:01. And that usually is the signal. Let's get started. So, welcome to the folks who are able to spend a little time this afternoon thinking about the future. My name is Roger, and about 2 days ago, I didn't have a voice. It goes totally gone. So it's going to be an interesting challenge to see if it will last for 2 hours this afternoon. So let's all keep our fingers crossed. I'm sorry about that. There may be a time or two where I'm going to have to clear my throat. Okay. In any case, the group this afternoon, unless it gets a lot bigger, a lot faster, we have a little more flexibility in terms of handling questions. But let's, for the moment, if you have an administrative issue, type that into the chat box. But if you have a question or something you want to talk about in terms of the webinar, type that into the Q&A. And maybe, all depending on how it goes, we might have a little time at the end for some further discussion. Okay, so, and I once again, I appreciate your understanding that occasionally people these days seem to be getting issues with their throat. So, times are changing. And in fact, not only are they changing, but they're changing a lot faster. I happen to have that TI-30XA on my desk, and that slide rule is still in my drawer, but in any case, I don't think anybody's going to argue the point that things are changing. And for that matter, it's also changing how we generate and use electricity. That's kind of the old way. And I imagine they decided to take that picture on a cloudy day because you can blame all that clouds on those cooling towers, but or smokestacks. But in any case, we're making it slightly differently these days. And you notice, well, these things don't work very well. And well, the windmills work on a cloudy day, but the solar, they don't work as well on a cloudy day. They might lose 20–30% of their possible output, depending on how many clouds. And of course, if it's not windy, then the windmills don't do a whole lot either. But in any case, things are changing. And we're going to talk about wild guesses as to just where we might be going. So, what are the trends? Well, for one thing, once upon a time, it didn't make much difference whether electricity was generated efficiently or not. But now it's making a bigger difference. And there's a big switch from fossil to renewable. Photovoltaics is the largest contributor to new energy sources as of last year. And that's a worldwide statistic, I believe, for sure in the United States. But I think the world tends to be a little bit ahead of us overall. So it should be true there as well. Admittedly, that solar and that wind stuff is a little bit cleaner than some of these other fossil sources. But the interesting thing is the predictability is the price we're paying for the cleaner sources of electricity. It is pretty predictable that at night the solar systems are not going to make any electricity. The windmills might keep blowing at night, but who knows? So it's something we have to deal with. Okay, and so what that means is we're going to have a lot more storage and a lot more maybe high voltage DC transmission lines to move this power from where it's being made to where it's needed. And in order to make all this above stuff work, we're certainly going to need more control and data analysis. So I'm going to mute for just a second and try to do a better job on clearing my throat. Please hold on, I'll be right back. Okay, hopefully that will be a little better. And indeed, it is just a little better. Well, anyway, here we have a plot of the cost of photovoltaic modules on a per watt basis from 1975 on up to 2015. And you notice it dropped quite a bit. In fact, by 2015, it had dropped below $1 a watt, even though back into the year 2000, there was a lot of solar people were saying $1 a watt's the limit because it costs that much just to make the module itself with the glass and the aluminum frame and the backplane. And forget about the silicon you're going to attach to it. That's just going to add more. But they were wrong, and I was part of that group, and I admit it, I was wrong on that one. So where are we going here? Well, 2020, the price was down to about 30 cents a watt, which means that since the 1975 period, the cost of photovoltaic modules has dropped by about a factor of 300. And 300 is a big number and one worth remembering, because who knows, there might even be a question about something like that on a quiz. Okay, so cost of solar is coming down. And not only that, but the shipments of solar are going way up. As of 2016, you can see that they were somewhere near, well, if we have 100 gigawatts. And if we move on a little further, I notice in 2021, we were up at almost 2,000 gigawatts or 2 terawatts. And even where the prefixes start getting big, and we're not used to using those big, we're kind of used to stopping at kilo or mega, and once sometimes giga, but now we're getting up into the teras for the prefixes. So the question is this, notice we have log scale on the left-hand side and a linear scale on the bottom. And since this thing is relatively straight, are we going to continue this exponential growth? Well, it's been happening up until 2021. And 2023 was a big year. 2021 was right in the middle of the pandemic and still did pretty well. So, and I just don't have data for 2023 yet, but the point is, the solar is now down to where people are noticing it. In 2021, you could do a residential install for about $3 a watt, and then you got your tax credit on that. And in 2021, utilities were doing installations for about $1 a watt. So that means if you can install something for $1 a watt and the operating cost is low, as long as it makes some reasonable amount of electricity, you ought to come out pretty well on that deal. So the $3 a watt's before the investment tax credit, which currently is at 30%. So that brings it down to $2.10 a watt. Okay, so once upon a time, this thing that it's used on wristwatches and space shuttles, but way too expensive for anything on the ground. That's not happening anymore. Here we go, United States, 2020, 3.1 gigawatts of residential PV systems, 16.57 gigawatts of total PV in the United States in 2020. So residential is about 20% of that. And well, globally, the added capacity in 2020 was 170 gigawatts. So that means that the United States is somewhere around 15% of the global total. So it's not that we're necessarily way up there, we're doing a significant amount, but globally folks are catching on. and installing a lot of this stuff as well. China, for that matter, in 2020 installed 48.2 gigawatts, which is about 3 times as much as we did. India was slowed down a bit by the pandemic in 2020, but they're picking up and installing relatively rapidly these days. Now we're looking at trends here. This is 2020. The numbers were smaller in 2012. And the question is, where are we going? And what kind of a role might the folks who are sitting in on this webinar be able to play in this? Well, for one thing, in 2020, there were 317,000 solar industry jobs in the United States. PV efficiencies continue to improve, reliability keeps going up, costs keep coming down. So it sounds pretty good for PV. What about the wind? Well, 85,000 people employed in the wind industry in 2022. That's more than were employed in the industry of drawing people's blood to check whether they're still healthy. Although these people are working outside, and who knows. In any case, the Bureau of Labor Statistics say there were 85,000 working in wind in 2022. And in 2021, worldwide, 97.5 gigawatts of wind power was installed. And 840 gigawatts is the cumulative worldwide total now for wind power, which is a pretty good chunk. But we're into gigawatts, not into terawatts. And you remember the previous slide that solar is in the terawatts. So wind and solar are relatively close to each other, but solar has taken a lead in recent years. There's also a lot of small wind turbines out there. Try as I could not find anything to update this 2014 data, but it's still 945,000 small wind turbines out there in 2014, and probably those same ones are there, and probably a few more as well. In any case, that adds some more megawatts. If we look at a large turbine, it can generate, if it's in a windy spot, and folks tend to have paid a lot of attention to where the windy spots are. And a large wind turbine can generate around 2,300 kilowatt hours a year per kilowatt of wind turbine. And that's just about what photovoltaics can generate if they're installed in the desert without quite as many clouds. More typically, the photovoltaic annual output for a south-facing array is going to be closer to 1,500 kilowatt hours per kilowatt per year. Construction costs on wind is not all that bad, not bad at all. So the only downside on the wind, just like the downside on solar, is it doesn't work well at night. You need sustained winds in wind generation, because remember that the wind pressure is proportional to the square of the velocity, and you have to have force times the velocity to get power. So there you're at the cube of the velocity, and in fact converting a linear velocity into a rotational velocity. But still, folks have gotten pretty good at it, as you can see. And gusty winds, the bearings in these rotating things just aren't that happy to have to deal with gusty winds. So nicer to have sustained winds. Here's what's been happening. Notice this growth seems to be more linear. What happened? Sorry. I've got a touchy mouse today. So you can see that the capacity has been going up relatively steadily, except it stopped a little bit from 2016. It's now picking up a bit again. And where is this wind action? Well, guess what? China. China's the leader, and you can see where everybody else kind of falls in line. It's interesting that Turkey has pretty good numbers for a small country. And so that's maybe about what we expected. And of course, with wind, you just can't have it everywhere. I mean, we get wind here in Florida a lot, but it's not sustained and it's generally kind of gusty. So we don't have a lot of windmills here. People have analyzed it, they've done the measurements, and they like the sun better down here. So in any case, if we look at the growth of worldwide energy production by source, it looks like this. And this is kind of an important picture because you notice the lines up top, those are the fossil fuels, the petroleum, the coal, and the natural gas. Notice that they've been relatively steady, started to pick up a little bit 2004 up through 2019. And now, notice the petroleum. Notice all of them, in fact, they all seem to be dropping off a bit. All right, while in the meantime, the hydro is going up a little bit. The other renewables, meaning basically wind and photovoltaics, although there's some other renewables in there, but not nearly to the extent. And hydro's been growing a little bit. And back around 2019, on a worldwide basis, the renewables passed the nuclear, and nuclear seems to be pretty steady, if not maybe declining a bit. So the question is, if worldwide energy use does not increase significantly as we start using things more efficiently and designing things more efficiently, once that green line gets up there, something's going to have to give way. And as long as the price of the green line is less expensive than the blue or the black lines, then predictably, the blue and the black are going to go downhill. And that's just a matter of economics. Forget about whether we're talking about conservation, whether we're talking about getting rid of CO2 production, whether getting, if we're thinking about climate change, anything like that. Right now, what we're looking at here is a picture of economics. And there's some interesting things to watch out for by 2029, by the way. That's 5 years away. So it's going to be very interesting to see what happens within the next 5 years. This is energy production, all right, kilowatt hours. Installed capacity in kilowatts, that's another story. But in order to get kilowatt hours, you need to have kilowatts. And a lot of attention is being paid to the number of kilowatts that you can store, so to speak. That is, you store your kilowatt hours and you have to get them back with kilowatts over time. So here's your 2022 picture. And you see that the percent of the total in 2022 of all total worldwide consumption, and this is by not the converted, but this is the basic content. For example, coal, if you burn that, about 2/3 goes into heat, thanks to the second law of thermodynamics, and 1/3 goes to electricity. All right, so even though we see 160 quads of coal, that 160 quads of coal can't make 160 quads of electricity. So we need to keep that in mind. So there's some numbers, the comparative numbers on source energy, meaning how much could you get out of it if you could extract 100%. Here's some, by the way, in case you haven't memorized, the quad happens to be whatever it says there in the lower left-hand corner of the screen, 2930710707172 kilowatt hours. So we're in the millions, billions, trillions, quadrillions. All right. So a quad is actually quadrillion BTUs. And if you want to get these numbers, go to the BP Statistical Review of World Energy. I like the idea that BP is actually reporting these numbers, and appears that their numbers are fairly reasonable from a petroleum company. They've changed hands slightly in the last couple of years, but BP is still getting credit for all the historic data. So anyway, here's the interesting thing that is now being used very commonly. It's called levelized cost of electricity. And normally it's in dollars per megawatt hour, but the numbers we're mostly familiar with are cents per kilowatt hour because that's what we pay for on our electric bills. So let's take a look at some of the common sources for this year. Natural gas, 5.6. What are you paying for electricity? We're paying about 15 cents per kilowatt hour. So somebody's making a little profit if it's all natural gas. Advanced nuclear, 11.8. Now keep in mind, the levelized cost of energy is based on the total cost of the source over this lifetime of the source, corrected for the change in value of the dollar from day to day and year to year. And this is all divided by the total amount of electricity that's produced by the source on an annual basis and corrected for the case where sometimes it becomes less efficient the longer it's in place. So advanced nuclear, if we're going to build new ones, that's kind of expensive. So we're going to compare that. And there's a factor here that's included here. It is what's the percentage? What's the duty cycle here? Advanced nuclear has pretty close to 100% duty cycle. Natural gas is relatively close. Onshore wind, look at that. The duty cycle there is a little less predictable, but 4.1 cents a kilowatt hour makes it worth building it anyway. Photovoltaics, 4 cents. Now, this is kind of a compromise between utilities being less and residential being more, but on average for the entire mix is around 4 cents. Hydro's at 6.4. And by the way, the first four are from the Lazard people, and they are economic type guys. And they are the ones who make all assumptions in terms of duty cycle and maintenance and all that kind of stuff that cost of fuel. But the star, here we go again, sorry, is Department of Energy in 2017 numbers. And so what's going to, did I miss something? No, okay. So what's going to change in the grid that's going to impact us? Well, for one thing, electric vehicles. And it's interesting, we all think about electric cars, electric hybrids, plug-in hybrids, but there's an awful lot of electric bikes and scooters and other interesting transportation gadgets out there that people a lot younger than I am are using. Energy efficiency. Almost everything is becoming more efficient. Zero energy buildings. We're going to talk a little bit about all these things as we go. And the whole idea of distributed generation and energy storage. These are all part of what we're looking at that's going to make this future. Somebody once said the future will be different from the past. And for my 80 years, that seems to have been a pretty good observation. So I have no reason to believe that's going to change. So let's take a quick look here at electric vehicles. Well, maybe a little more than a quick, because there's a lot going on there, and there's a lot of opportunity here for engineers. Basically, there's two types. There's the all-electric, and there's a plug-in hybrid. The all-electric generally has a range somewhere 400 to 400 miles. And of course, all this is going to change as we move into the future. Battery storage capacity somewhere in the 30 kilowatt hour to 100 range. And mostly lithium-based batteries now. You all can read all this. I'm not going to read this fast. I'm just going to give you a chance to look at this, save my voice a little. And The electric, this plug-in hybrids, happen to own one. We've had one for almost 6 years now, and it's been a fine automobile. We don't drive very much, maybe 15, 20 miles a day mostly. So we buy gas for it for the times when we do use up our 50 miles of electrical range. But we're averaging somewhere around 1,500 miles per gallon of gas. So that means most of our driving is on electric. If you have a hybrid car, you can do still about 350 miles on, well, I'm sorry, for the plug-in hybrid, that the gas engine will give you another 350 miles. So you got 400-mile total range. Lithium batteries, most of them. And how long to charge? Let's take a look at that. National Electrical Code 625.2 recognizes these electric vehicles, but golf carts and forklifts that are not on the road don't count. And I don't know yet what they're doing with all these electric scooters and bicycles and so forth. I need to read up on that. But clearly, I think everybody is going to see, maybe in the north doesn't have quite as many of the electric bikes and stuff for the winter time, but down here in Florida, we've seen a lot of electric vehicles, especially on university campuses with the young folks. You can't be an electric vehicle unless you use rechargeable batteries. So therefore, it is not okay to use these. And in fact, even in my hearing aids, I have rechargeable batteries now. So for hearing aid battery manufacturers, I'm not sure where their batteries are going these days. So let's just, again, we've been talking economics. Let's take a look at fuel cost per 1,000 miles, okay? And of course, the hard part here is what's the gasoline price? I mean, it was up around $5 a gallon there for a while, 2.75. So here is where you put your own numbers in. But if it's 2.75 a gallon, then the numbers are going to look like this. If you drive a full-size SUV, you get about 50 gallons of gas because you get about 20 miles a gallon. At 2.75, that's 137.50. Okay, if you have a baby-sized SUV and only get 30 miles a gallon, well, then you're going to pay about $91.67, give or take a few cents for your 1,000 miles. And if you've got a hybrid sedan, like one of these, they get about 18.2 gallons because they get about 55 miles per gallon. So there you got $50 in fuel cost. If you got plug-in hybrid or an electric vehicle on electric only, at 15 cents a kilowatt hour, you're down to 37.50. Now, my grandson is on a time of use rate with his electric vehicle, and he's paying a nickel a kilowatt hour. So again, you got to put in your own numbers here in order to get some numbers that apply to your neighborhood, all right, or to your automobile. So in any case, if you're electric only, you're going to get by for $37.50 or likely less, unless you go to some of the other fast chargers where they charge more for a quick charge. But if you plug in patiently overnight and wait for it to charge whenever the utility is willing to sell you electricity cheap, then you can get by pretty cheaply. Okay, if you take these plug-in hybrids and go half and half on gas and electric, then your cost of transportation goes way up to $46.25. So again, economics, why are people buying these things? They're finding out from their friends. They're also finding out performance-wise, a lot of other reasons. There are reasons out there too, that nasty, heavy battery pack making those tires wear out faster, and all that terrible pollution, none of which is greenhouse gas. But it does kind of find its way deposited along the roads, and it's not a good thing. I don't claim it is good, but if you happen to think that greenhouse gas levels are getting a little scary right now, then you may be one of those who would buy an electric vehicle just because it's the right thing to do, rather than because it's a whole lot less expensive and because it's better performing automobile with less maintenance costs, and on and on and on. I'll let the manufacturers advertise their own product, but that's been my own experience. In any case, a level 1 charger, it's used 120 volt outlet, and charge that around somewhere around 1200 watts. On a 15 amp, 120 volt circuit, the maximum you're going to pull is 12 amps, which means you'll charge at about 1440 watts. So again, the word about, and 1440 is probably a more realistic charging rate for a level 1 charger, just because they're not going to blow the fuse on a 15 amp circuit if it is dedicated to the car. And if it's got a few lights or something on it, it's probably not going to mess with that either. And if it's plugged in on a 20 amp, 120 volt circuit, then there's a number of things. You've got an extra 4 amps you can use for other things. That lights up a house with LED lighting. Level 2, somewhere in the 3,000 to 7,000 watt range. Now, even since this slide was made, they've gone up to 100 watt chargers on level 2. Not 100 amp, which is not really 100 amp. It's a 100 amp breaker with 80 amp charging, but but 80 times 240. I'm sorry, is 19,200 watts. So that's a lot. So in any case, here's what some of the circuits use, depending on, whether it's 7,000 or 3,000. But if you've got maybe a more common charger now, it'd be a 9,600 watt charger. And that 9,600 is going to be pulling 40 amps. So that's going to need a 50 amp fuse or 50 amp circuit breaker. All right, so the 9,600 is, and the 40 amp is a little more popular simply because most residential services can handle that extra 40 amps. And we're going to take a look at that. It's nice if you don't have to do a service change in order to add your electric vehicle. So one of the things that the engineers are going to want to be able to do is do a legitimate service calculation or a legitimate load calculation to determine whether or not you need a service change. Why guess when you can calculate it out fairly precisely? Okay, so anyway, level 2, level 3, on the other hand, that's the big one. That's fast charger. We're looking at 125,000 watts. And this one is usually connected to a 3-phase service. And if you're on a 3-phase service, that means you're not going to be residential. So that's where you're going to stop if you're on the turnpike or the freeway on a long trip. Maybe stopping at McDonald's for lunch or something. Okay, higher charge rates are on the horizon. No, the higher charge rates are already here, but even higher on the horizon. So how long does it take to charge? Well, level 1 charger, 1,200 watts. You can usually do about 4 miles per kilowatt hour, but maybe to be more realistic, say 3.5, and allow a little bit of that electricity for your air conditioning and your radio and a few other things that you might have on in your car. But in any case, it's also possible that you'll be doing 1.44 kilowatt hours per hour instead of 1.2. And so again, you use the numbers that work where you are. The multiplication is still straightforward. We're looking at somewhere around 5 miles an hour for charging a car with a level 1 charger, and that's pretty consistent with what we're finding over the last 5, almost 6 years with our car. roughly 5 miles an hour for charging. All right. Now that means if you get 8 miles per kilowatt hour or 12 or 15, like with a bicycle, then of course you're probably not going to charge at this rate either. What do we do with level 2? Well, if you're charging at 5,000 watts, and again, put in your own numbers, what that does is, and of course, this is a nice number because 5,000 watts in 1 hour is 5 kilowatt hours. And this is somewhere around, if you look at the 1.2 kilowatt hour and then multiply the 5 times 4 and you get about 20 miles per hour charging. If you've got that 9600 watt charger, then you're looking more like 30 miles an hour of charging. So if you drive 30 miles a day, plug in your garage overnight for an hour and you're good to go for the next day. If you've got a lot of storage in your car so that you can charge for more than an hour, then you could drive more than that in a day and still make up for it. That's important to know. Level 3, 125,000 watts, half an hour, you got about 80% of your charge returned and a little over 200 miles in a half hour charging. So what would you like to have in a good charger? Well, the basic one is going to be compatible. It's going to have communication, tell you how full your tank is at the time, how much you've been charging with, how long is it going to take to charge, is it safe, is it going to shut off when the battery is full, how much is it going to cost to install? Maybe it's already there. That's a pretty good price. Most garages have a spare 20 amp outlet sitting somewhere for use by whatever. Of course, whatever it is has to be code compliant. Just for the fun of it, you see the two larger holes there at the top of this thing. Therefore, the L1 and L2, the hot leads, which can be either 120 or 240 volts. The charger doesn't care. It all matter what's plugged in, or the car doesn't care anyway. This one happens to be 120, but if you find one of these out in this parking lot somewhere, more than likely it'll have the same configuration and be 240. The larger round one at the bottom is the ground, and the two smaller ones are your communication, which are kind of important because that's what prevents you from driving away if your car is plugged in. They simply talk to the motor and say it would be good if you'd wait a while. Otherwise, we will not be able to recharge you tonight. So, oh, and by the way, the host has a copy of these slides in PDF format. If anybody wants to order up a copy, he'll be telling you how to do that in the chat box. So keep that in mind if you don't have your copy already. Advanced chargers will be bidirectional. That means they'll have an extra inverter in the car such that if you want to sell electricity back to the utility or use it in your house, if you have a way of disconnecting from the utility in the event of a utility misfunction and the utility goes down, there are all sorts of interesting things that are coming up in the bidirectional mode within the next 5 years. In some places, this is in place. In Florida, it's not quite yet, but one day it will. My California, of course, are ahead of everybody. My understanding is that North Carolina has this option. But in any case, bidirectional, adaptable, portable, all these nice features that we want on Advanced. But the main thing is your car is going to be able to imagine 100 kilowatt hours. That's a lot. And if you just keep your car parked in the garage after a nasty ice storm, and if it's connected so that it can sell back to your house, then you're going to have electricity for quite a long time. And if you have some solar along with that to make some additional electricity along with what you got saved, you can go for a long time. So what are some typical chargers? One might look like this. This is your level 1 charger, and that connector is the J1772. And that's the one that charges at 1440 watts. Here's a level 2 on an outdoor pedestal. I think this one's at a Nissan dealership, believe it or not. And here's the level 2 that you might hang on your wall in your garage. And here's level 2 you might find at your local library. And here's one you might find at your local university. Or who knows, maybe in your garage. So what are the codes and standards here? Well, NEC 625 is on electric vehicles. And NEMA has some standards for the various connectors, which is convenient. Otherwise, there would be an awful lot of different connectors out there. And the SAE has the J1772. That's the connector you just looked at. That's pretty common for anything that just uses level 1 and level 2. The level 3 charger is a little bit different because we're looking at currents up in the neighborhood of 100 amps DC for that. There's the open charge point protocol. And this is important because this, as a uniform code, it enables communication among different chargers, so that if you want to put more than one charger on a single circuit, you can do that. We've already established that it's highly likely that within 1 or 2 hours, no level 2 charger will totally fill a car for the day. If you have 2 cars, then you can park them side by side, each have its own charger plugged in, and the chargers share one way or another the electricity that comes in, so that they're not both running at the same time. They might both back off their charging rate to half of what it was, or they might do the, okay, I'll do yours now or mine now, and you can do yours in 2 hours when I'm done. Or give me an hour and then you can have an hour and then I'll take an hour until we're done, or however that might go. So there's a lot of interesting stuff out there, and the software is going to be lots of fun for those who like that kind of stuff. UL 2202 is the UL standard for EV charging, and if you have an extra $1,000 handy, you can pick up a copy of that. And if you were interested in manufacturing EV chargers, it's highly likely you would buy a copy of this. Make sure you got it right. 2231, personal protection systems for EV supply circuits. That's interesting because EV supply circuits, well, okay, they do have personnel protection systems. But for the most part, plugging in a car is not much different from plugging in almost anything else. Anyway, you can read more about it. Here's your reference if you want to read a little more about it in the Wikipedia. So what if we want to add a charger? And this is what you might do for a single family residence, okay? And we're going to go through the calculation here. The old faithful 3 volt amps per square foot for 1,500 square foot residence. We got 4,500 volt amps. We have a washer, a dryer, a refrigerator, and 4 appliance circuits in this place. And each of those with their NEC rated capacity, they all add up to the total of them is 13,900. Why didn't I list them separately? It would have gone off the bottom of the screen and you wouldn't have been able to see it anyway. Then there's a water heater in a range, another 16,500. So we got a total of 34,900 volt amperes. And if we're adding, we can take the first 8 kVA at 100% and the remainder at 40%. And then we haven't talked about the heat or the air conditioning yet. So if since they're non-coincident, if the heat load is bigger than the air conditioning, then that's going to be 6,500 volt amps. And then the charger gets added in, and you have to add that in at 125% of its rated load because the assumption it will be charging continuously, which means you almost have to have more than one vehicle because continuous means charging for 3 hours. And if it only takes an hour or 2 hours, then that isn't continuous. In that case, a 40 amp circuit needs a 50 amp circuit breaker, a 40 amp charger. All right, so you have to add that in at 9600 volt amps to all this rest of this, just like you did for the heat or the air conditioning. And then you get a total feeder load of 34,860 volt amperes. And divide that by 240 volts, 145 amps. So, pretty straightforward calculation. Whoops. And as long as your 16 service is 150 amps, you're good to go. As long as you have a 2-pole 40 amp circuit breaker in your main distribution panel. Because it's 7680 volts or volt amps, 7680 divided by 240 happens to be 32 amps. And that's why it's 7680. 32, 125% of that is a 40 amp circuit breaker. Okay. So if you can do that, you're good. Otherwise, you may have to do a line side tap or some other way to get it in there. Or if your panel is way too small and way too old, you might want to switch it out for 42 position and have room for 2 EPs if you bump it up to 200 amps or something. Or if you don't pump it up to 200 amps, depending on how your chargers communicate. So anyway, here is your calculation, pretty straightforward. And thought we put a little bit of meat into this otherwise conjecture type predicting what's going on. If we want to do an alternate calculation for writing a charger, you could actually see a lot of things are more efficient now. So 220.87 says you can simply look at the maximum peak demand over the past 12 months. Well, of course, the residences don't have measurement of peak demand. Most residents are on straight kilowatt hour, straight energy basis. But if you have an occupancy that is on a general service demand rate, then you can check up what the demand is. And for my condominium here, for example, we've got 1,600 amps of house load, not the units, but just the hallways and the elevators and the air conditioning and stuff. And we're only using about 290 amps of that 1,600 amps. All the rest of that is stuff left over that could be used for charging electric vehicles using the 220.87 method. Okay, so in any case, 220.83, 220.87, use whichever one works, whichever one will give you the best answer. Where do you tie it in? Maybe it goes right to your main distribution panel, but maybe it has to go elsewhere. In any case, NEC 240.21B2 tells you that you could have a charger branch circuit over current protection, could be within 25 feet of the tap, as long as the current drawn by the main overcurrent protection is at least 33 1/3% of the feeder. So usually that's going to work because if you've got number 8 wire and 55 amps, then 0.333, that allows for a 175 amp main breaker. If you had number 6 wire going to your branch circuit to charge your car, then you could have a 225 amp main and still be 25 feet away. So a good old National Electrical Code, they've been thinking about us and they're all ready. So anyway, this is something that could go in a condominium, but it's not all that good of an idea, and that I'm going to just skip over that kind of quickly. NEC 625 gives you lots of information on Oh, by the way, that condo charging thing, after doing more analysis, I've concluded that probably not the best idea in the whole world to tie electric vehicles into the individual services in a condominium. The reason for that is because if you have a 1200 amp meter center, you probably have 30 or maybe 20 or so units, and you have a diversification factor of in the 30% range. And as you start adding 100% of the chargers, you start bumping against the maximum in that entire meter center relatively quickly. And that's why I wanted to skip over that kind of quickly, but keep it just as a reminder to share that information with you. If you do that calculation properly, you could end up with a problem. So in any case, an EV storage battery is one that's sealed and does not release gas. Okay, that's important because lead acid batteries release gas while you're charging them, but lithiums don't. And any future technology battery is also not about to release any kind of gas that would apply here. If they're fixed in place, it means you need a tool to remove it. If they're fastened in place, you can remove it without a tool. And it's not a bad idea to fasten in place one way or another. Otherwise, they're just hanging there from the wall. And it's kind of a strain on the plug that's plugged into the wall outlet. Nominal AC voltage, you can see there are a lot of them all the way up to 1,000, and DC up to 1,000 are also large, allowed. So there are a lot of voltages allowed. And electric vehicle supply equipment and wireless power transfer equipment is also out there. I'm not seeing much of it used. I saw one recent ad for a battery pack that you simply take out of the car, but I don't think they're using WPTE either. But what I do understand is that they use a higher frequency because transformers with large air gaps at lower frequencies are not very efficient, and that's what was being implied here if we have wireless power transfer. So that's something people are playing with, but not much of it is out there. But NEC is on top of it. And then part 20625 gives manufacturing specs. Some more 625, you can read this stuff, just you know that it's there now. The important one is 62541, because that's the one that defines what we just used in that calculation in the residential situation. You're doing 100% of your continuous load, that's what you've already shown, and then 125% of the car charging. Excuse me. Okay, so in 62548, this is what we were talking about. Interactive systems. It's already there. They simply have to comply with NEC 702 and 705, which means UL 741, and that's another story. But it's out there, it's ready, and NEC is ready for it. Okay. And let's finish off this 625. Whoops, back up. It's more of a cute little picture of where we're headed for chargers. Okay, let's move away from EVs. And let's move toward the fact that we're about an hour into this almost. So let's take a look at what's going on with energy efficiency. Energy efficiency retrofits and electrification. My, millions of buildings, most of them can be made greener. Again, everybody can read this. Let's see, I'm going to do something here. Let's see, we got 10 participants. I'm going to ask a question here. And I'm going to ask you to raise your hand. How many of you actually know what the seasonal energy efficiency ratio of your household air conditioner is? Have any approximate idea of what it is? Just raise your hand. This is a practice in finding where is the button for raising a hand. And if you go to the go to the participant box and move your arrow next to your hand, there should be a hand. Wait a minute, what's going on? Maybe there is no hand. Well, I think I guessed wrong on this. Yeah, I mean, everybody's platform is a little bit different. This one seems not to have the hand raise option. Oh, there's one. It is there. Okay. All right, Herbert knows his. Anyone else? Herbert, if you can unmute your mic and tell everybody where to find the raise their hand sign.
So on the bottom in the middle.
Bottom in the middle. All right. Let's give just a few more seconds. All right. While you're online, Herbert, hopefully I don't. I'm going to call you by your name that I see written on the screen. Herbert, do you have any idea what the SEER of your air conditioning is?
Nope.
Okay, and most people don't. But I can tell you that back in 1980, when Florida first adopted its Code for Energy Efficiency in Building Construction, you had to have a minimum of 8 with the SEER. All right, now, of course, what's the SEER? That's seasonal energy efficiency ratio, and it's measured in hybrid kind of units because it's in BTUs per kilowatt hour. And really it's in BTUs per watt. So if you have a 1 ton and if you get 12,000 BTUs per watt, then to get those 12,000 BTUs is going to take 1,000 watts. Okay. So that's the definition of the seasonal energy efficiency ratio. The units are BTUs per watt. And so the 12 is not bad. 8, of course, was the minimum back in 1980 that you could install. We're going to take a look at what we can do in 2023. Okay, let's move to a few more. How about LED lights? Does anybody out there have LED lights in their house? Or headlights on your car or wherever else? Now this one I'm just checking to be sure because everybody's going to raise their hand on this one, or else you're living somewhere in the forest. And have okay. So yeah, I mean LED lights and you all have an idea of how much more efficient LED lights are in terms of lumens per watt than incandescent lights. If anybody has a good number to throw out, go ahead. Just unplug your mic. I mean, open up your mic and shout it out. What's a typical improvement in efficiency of LED over incandescent? Well, factor 10, depending on the size of the incandescent bulb. So, how many buildings out there have been calculating those 3 watts per square foot based on incandescent lighting and now have replaced it all with LEDs? Think about your computer versus the one that used to use vacuum tubes. We've got a lot more efficient stuff out there now, it's the bottom line, okay? If you have better doors and windows in, makes a big difference. Even hurricane glass, which we put in a few years back, boy, not only is it tinted, so it keeps a little more of the sun out so that we don't get the full 1,000 watts per square meter, and keeps a lot of noise out, and hopefully it keeps the hurricanes out. So far, so good. So, you know, sometimes you do better doors and windows and you do things for one reason and you get some extra benefits. And the air leaks, plugging them, we're going to talk a little bit about air leaks and insulation and landscaping and all these things that can be done. And you get your money back on your electric bill by not paying for, or your water bill, by not having to pay as much because you're using these things more efficiently. Here's the air conditioning. This is a Q&A. Let's take a look at Q&A. Wow. You don't live in Florida then, Timothy. I'm impressed if you don't have an air conditioner. You must be up north. Maybe in New England, could that be? Maybe you could, New York State. Okay, yeah. Because even the people I know down on Long Island, they all have air conditioners. But I can imagine if you're up in the Adirondack somewhere, you might be without air conditioning, and that could be really nice. Thanks for coming back on that, Timothy. Okay. Oops, there's another Q&A. I better go back. Oh, I know what I didn't do. I didn't click my things I have to click. Okay. Let's take a look at heating, ventilation, air conditioning systems. How many have seen a thing like this? This is a mini split. No air ducts. Just refrigerant lines between the compressor unit and the evaporator unit. A little clumsy, maybe. But look at the SAER on this, and this is a heat pump, so this is heat or cool. And SAER on these things goes up to 33.1. When the last time I looked, maybe more now. That's 4 times more efficient than these things were required to be back in 1980. So have we made some improvements? Yeah, it's out there, ready to grab, and it pays for itself. Do a payback analysis. Here's another interesting creature called an energy recovery ventilation unit. Not sure whether you've heard of those or not, but what this does is it's a countercurrent heat exchanger, and it sucks in outside air to replace any inside air that might be vented out, say in a bathroom vent fan or a dryer vent or something like that. And if that outside air is hot and humid, and in fact, it's replacing the indoor relatively cool and dry air with hot and humid air, then that indoor dry air going back outside alongside of the outdoor humid air also does some dehumidification. So therefore you need a condensate drain on this thing. It's called energy recovery ventilation. The efficiency on this thing is that you recover roughly 90% of the heat or cool that's being discharged to the outdoors with this unit. And that's compared to 0% recovery if it's coming in a crack in the window or a crack in the door or anyplace else. Okay, and here's the cousin of the energy recovery, the heat recovery. And this one happens to not have to worry about humidity, so it doesn't have to have a condensate drain. This is sensible heat only, which would probably be a little more applicable up north. And of course, when you do these things and you get more fresh air in because you don't care as much now if you got 10% loss only, then all of a sudden the air inside gets a little better and your breathing becomes a little bit better and you don't cough like I'm doing right now from my condominium room. I'm coughing for a slightly different reason, but still, no question the air could be ever so slightly better in here. All right, so here's a couple of things you can do in the heating, ventilation, air conditioning system neighborhood when the time comes, when you're ready. And these, the ERVs and the HRVs are sometimes very handy for basements. But if you got a spot where you can put them in upstairs, not a bad idea either. Just check out their specs. Then there's domestic water heating. Once upon a time, solar water heating was the way to go. I can tell you, I mean, we put in a solar water heater or 39,000 BTU unit per day back in 1975 on our single family detached residence. And that thing, once we put a timer on it to make sure that the backup electric would not work during the day when the sun could do the job, we were getting at least 90% of our water heater or hot water from the sun. And that was a really good deal because we got that water heater on a special deal on a promotion for $400. I don't think you'll find one for $400 out there now, more like 6,000. So in any case, back then, of course, PV was out of the question. But now you saw the levelized cost of electricity for PV now. It's less than the cost of utility electricity. And so I invite you to do an analysis with what you would pay, but rather than on just a plain old electric water heater, well, try it on one of these things. A heat pump water heater. It's also named a hybrid water heater. And the reason is because in the heat pump mode, they work like a heat pump. So they extract heat from the local environment and dump it into the water. And of course, when you take heat out of the environment local to the water heater, what happens to that local environment? Well, it cools down. So you get a secondary benefit if you want that space, which if it's a garage, you probably do want it cooled off a little bit. So in any case, you've got a 3.5 kilowatt hours of heating for every kilowatt hour of electricity you use. Not a bad deal. They're a little slower. They're limited to 4,800 BTUs per hour produced by the heat pump part, and that's why they're called a hybrid, because they still plug into your 30 amp outlet, and they will pull the 4,500 watts of heating if you really want to use that hot water in a hurry and you can't wait a little bit longer for it to heat with the heat pump. So you have kind of an average here, but in any case, if you get one of these things, it'll probably look like this. It's a 50 gallon. If you have a family of 4, this would be a fine thing to analyze next time you change out your water heater, and you're probably doing it about every 10 to 15 years. So give some thought to these. These things can save a whole lot of money if you can just reschedule your hot water use ever so slightly. It's just not everybody taking a shower at the same time of the day will make a big difference on the overall efficiency of operation of this unit. Then there's the smart irrigation controls. They can do so many nice things. They can override the automatic controls from far, far away. You can be off on vacation and open your phone and say, okay, what's going on at home today? And these things, they can adapt for weather. They can adapt for grass and the vegetation type, soil type, shading, seasonal and daily temperature. And one of them likes to communicate by way of Wi-Fi. So isn't that nice? You could easily save 70 or 80% on your watering bill. And if you're watering 24, well, not everybody's watering 24 months or 12 months a year. But if you do water 12 months a year, this is definitely worth giving some thought. And even up north, depending on how much you water, do the math. You guys know how to do math. You know how to do arithmetic. See if payback on this thing is going to work. And maybe you just got some extra money and you want to do it because it's the right thing to do. Who knows? So many reasons we have for doing things. So if you have water pump, or even if the water that you're saving has been pumped by somebody, more than likely, so it saves somebody else some electricity, and of course that's all factored into your electric bill, or maybe some is subsidized by the local water company, who knows. So anyway, there's your smart irrigation. What about zero energy buildings? Oh, they must be kind of nice. No energy at all, no air conditioning, no stove, no lights, no energy. No, that's not what a zero energy building is defined as. A zero energy building is something for which the energy exported by the building itself will be renewable energy, and it will equal the amount of imported from other sources, some of which might also be renewable. All right, so we have a definition, we have a site boundary. Within that site boundary, we have something. Maybe it's a building, a campus, or even a community. All right. And within that site boundary, we have a way of producing renewable energy. Oh my goodness, hmm, that arrowhead is sitting there all by itself. Wonder what it's for. Oh, this site happens to buy some energy, and maybe there's some renewable, but the amount of renewable generated in the little yellow box is greater than the energy delivered, greater than or equal to the energy delivered in the pink box. Okay, and when the green box, well, olive box, the box underneath the delivered energy box, the exported energy box, when the two are equal, you have a zero energy unit. Now, it's not quite that simple, because the energy has to be all compared apples to apples, or kilowatt hours to kilowatt hours, however you want to do it. And so the way you need to do that is take into account these things called source energy. Okay, and source energy units have certain energy content. For example, here we know what a barrel of oil will do: 58,000, 5,800,000 BTUs. But that's 5,800,000 BTUs stored in that barrel of oil, but how many of those can be recovered? And the same thing for the fuel oil. How many of the 137,400 can we recover if we want to make electricity? Okay, so first we need to make a list of the sources that we're going to have involved with this building. So let's do a simple example. Here's one they might want to rebuild. And let's say the new building is going to use 7,500 kilowatt hours of electricity and 500 therms of purchased natural gas, maybe. And this is just for illustration, because more than likely it's just going to use electricity. But let's assume it does use electricity and some gas, because maybe it's from the far north or something like that. So in any case, here's why we need to do the math. Converting electricity to BTUs, 7,500 kilowatt hours, have to multiply that by 3413 BTUs per kilowatt hour, and you get 25,597,500 BTUs. That's how much electricity you're going to use. Now, how many BTUs does it take to make that electricity? Well, it takes a lot more than that. In fact, it takes 3.15 BTUs of source energy to make 1 BTU of electrical energy. So in order to convert this to source energy, we multiply by 3.15, get a new number in the 80 million range. Okay, so there's your electricity that you're going to use in terms of source energy: 80 million BTUs a year. Natural gas, 500 therms. If we convert that to BTUs, that's 54,500,000. And now that 54,500,000 plus the 80,632,125, our total source energy for the year in this house is 135 million. Okay, so all we need to do is offset it with some kind of renewable electricity. Why don't we do it with photovoltaics? Okay, and then we'll see how big a PV system, whether this is realistic, whether it works, what's the deal. Okay, so here you go. If we're in a nice unshaded spot facing south, there's a very nice simulation program available from the National Renewable Energy Labs called the System Advisory Model, SAM. And SAM will tell you that if you're looking south with a reasonable solar system, you can make about 1,500 kilowatt hours a year per kilowatt. All right. So if we convert this 1,500 kilowatt hours to BTUs, that means every kilowatt of solar will give us 5 million or so BTUs per year. All right. But now we have to convert it to source energy by multiplying by 3.15. So now we're up for every 1,000 watts of solar that's installed. What you get is 16 million BTUs a year. All right. So we know how many BTUs a year we need in source energy, 135 million divided by 16 million, 8.38 kilowatts of solar. I can tell you that the thing I do when I'm not doing webinars and sleeping and eating and things like that is I sign off on plans for residential solar systems. And in the past 4 years, we have signed off on approximately 5,600 of those and about 56 megawatts. And guess what? The average residential system that we are signing off on down here and people are installing is roughly 11 kilowatts. So is it possible? Yeah, the proof is in the pudding. You absolutely can do that. So, and of course, this is all trade-off stuff. If you don't want to make it with solar or wind or whatever, maybe you can add some more insulation. Maybe you can do something else to make it even more efficient. But this is just one example to show that yes, this is a realistic thing, and zero energy dwellings are a thing of the present, not a thing of the past or the future. Well, yes, of course, if they're present and people are happy and people are going to be talking about them. And I have several friends who have them and they're thrilled. And I wish I could have one, but I'm stuck in a 43 unit condominium and I can't do that. But I'm sure I'm happy to be able to help other people do that because they are absolutely thrilled when they only have a maintenance fee on their electric bill, but no charge for consumption. So how much space does it take? 200 watts per square meter roughly for an array. Okay. And so we need 8.38 kilowatts. So how many square meters? That's 41.9 square meters, 451 square feet. That's not a whole lot of square feet, is it? I mean, on an 1,800 square foot house, some of that roof will be facing in other directions. But even if you point east or west, you're still going to get about 75% of what you get by going south. So you can still do it. You just need a little more space. So interesting, possible. 300 watt module, that'd be 28 modules. And 300 watt modules, there aren't very many 300 watt modules sold anymore. Most of them are 400 modules, 400 watts. So that makes more like 21 or 22 modules instead of 28. Of course, they're a little bit bigger, but still 20% efficiency, that's the magic number. That's what determines how much roof area is going to be needed. So obviously you can't put any old thing on the roof. You probably can as long as you don't put too many, but if you get just the right size with the right aspect ratio, then for some of the fancier roofs, you can do better with certain modules than with other modules. What are the trade-offs? Well, if you can make the building more efficient, then you don't need as much solar or wind or other stuff. So it's just a trade-off. Different orientations for PV. Again, trade-off. See how it applies to the cost of buying a new air conditioner or a hybrid water heater. And then again, if you had an electric vehicle or two, turns out about 1,500 watts of solar will pretty much take care of the electricity that let me try to get rid of that. If you've got another 1,500 watts of solar, that'll pretty much cover the electricity for an electric vehicle. So that still is realistic for the average residential roof. Here's an interesting chart. You're going to build a zero energy building in any of these 6 cities. The middle line is the amount you're saving on your electric bill or on your energy bill compared to how much you have on your initial investment as factored into I don't remember what the mortgage costs. But again, you have to use the prevailing numbers here. That mortgage rate may have been at 4%. But in any case, big time savings. And if you start doing the time value of money and trying to figure out what you might be paying for electricity or any other number of things 10 years from now, these things start to become looking even more attractive. And you're the engineer, so you get to do the math for the people who are thinking about it. And what fun that is. Energy storage, what about it? Let's take a look at the time here, make sure we're not running out. We're gonna probably do okay. What about energy storage? Well, we've had small stuff around for a long time, but the real energy storage, honestly, actually started out with nuclear power plants about 60 years ago or so. When they had extra electricity at night, they used to pump water uphill, called pumped hydro, and then let that water run back downhill again during the day when they need more power again. That way you didn't have to back off on the power output of the nuclear station. I think most engineers understand that nukes are not terribly stable. And once you get them stabilized, you want to keep them there. And that means you want to keep generating at a constant rate. So, there are a number of different standalone PV systems where there's been energy storage. And that particularly standalones were very popular before the year 2000. They were the dominant in the marketplace. But after the year 2000, then all of a sudden we started connecting these systems to the grid and selling back any extra electricity once the batteries were full. And the standalones were used for backup. Worked great in 2006, 7, 8, whatever, for backup systems for hurricanes in Florida. And it works fine in New York State for backup for ice storms. So people are buying these things, and we've learned a lot from them on how to do energy storage properly. They've been a little costly, and they're mostly treated as an insurance policy because if you can save a freezer full of filet mignon, more than likely you get your money back on sooner or later with by keeping that freezer cold. If you're a vegetarian, who knows what kind of vegetables you might have frozen, but still, you have to define your convenience and loss of food or whatever else might be, or if you have a health issue that you need extra power, even though battery backup PV systems are not classified as emergency systems, they can take over when you run out of gas on your emergency generator. So, or they can prolong the amount of gas that you're the length of time before you run out of gas, because if your PV provides the power, then you don't have to turn on your gasoline generator if you have a health issue, an emergency type system that has to have electricity. All right, so they've also been a little complicated, and they needed some programming on site, and so people mostly just had a meter, a main disconnect, and a main distribution panel. Most people didn't bother with the PV or the battery backup. A small percentage of people who had whatever reasons they had. But now, pretty dramatic, huh? Here comes the Tesla battery. Actually, there's some other batteries out there too, but they work pretty much along the lines of the Tesla. And here's the deal. You can start out with the meter and then put in one of these things, main disconnect with feed through lugs. And in that main disconnect, which is really a distribution panel as well with a main breaker in it, you've got some interruptible loads there that if the utility goes down, you're out of luck with whatever those might be. Unless, of course, you decide to wire it differently and have a whole house back up, and that's another story. But this is how it first started out as a partial backup. You put this automatic relay in because the last thing you want is if the utility is down and you turn on some kind of other generation, you want it disconnected from the utility because for one reason, if that generation feeds the utility when some poor utility worker is trying to rewire a down distribution line and gets a surprise on a shock from somebody's PV system down the street, that is not appreciated. So we have these things called mid-circuit, or not mid-circuit interrupting relays. It's basically just an automatic contactor that senses the presence of the utility, and when the utility goes down, it opens these contacts. Now, on the other side of that relay, here's your main distribution panel with the main circuit breaker, and it has uninterruptible loads in it. And now we can't see the reason yet until we bring in a combiner panel, which still doesn't have anything to feed the interruptible loads. But if we add a little bit of solar, then we do have interruptible loads if this PV inverter can keep operating when the utility goes down. And that's an interesting. There are some out there that'll do that. They're called sunlight backup systems. And a few people have been installing them, but most of the people who want some backup, they want the assurance of batteries, and they connect down here. And you notice the Powerwall's got a rectifier and inverter, so it's basically an AC unit, AC in, AC out. So you got some losses on the AC to DC conversion for charging the battery, and you have some more losses when you discharge from DC to AC. But those losses are relatively small in the 3 to 5% range each direction. So your round trip efficiency on this thing can still be somewhere pretty close to 90% and sometimes higher. Okay, so here's energy storage at the local level. And of course, who says you can't make something bigger than a Powerwall? So anyway, here's the results. Yes, utility and no sun. You still have utility power going everywhere. But if the utility goes down, then you don't have power to the interruptible loads, but you do have power to the uninterruptible. And have power until the battery runs dry or until the sun comes up. And just like that, piece of cake. So how do you size it? Well, all right, this is a long story and it's crazy to try to explain how to size a system. But this, and in fact, this isn't even the way people do it. It's the way maybe people could if they wanted to. But now, because the price of PV is so inexpensive, there's no reason to try to limit the size of your PV unless your roof is going to limit the size of your PV. So let's say your maximum monthly kilowatt hour is 1,200, okay? And let's say that's about 40 kilowatt hours a day on average, isn't it? All right, that's the first thing we want to do is see what the daily total load from your biggest utility bill. And then how much of this are we willing to let be interruptible? And of course, there are lots of different options because if you don't want anything interruptible, something's going to be interruptible anyway if your battery runs low. And you may have to turn something off manually, but you can give everything a chance at first and have a pretty good idea when you're going to have to start turning things off, or you can buy fancy distribution panels now that will do load management for you. So a lot of different options here. And so don't leave thinking this is the only way to do it. There's a lot of different ways. This is one way. If we leave out the hot water, air conditioning, dryer, then maybe you're down to 20 kilowatt hours a day. Okay? For everything else. And wouldn't it be nice then to make 20 kilowatt hours a day with your solar? Well, we know you can do that. An average array will do 1,500 kilowatt hours per kilowatt a year, so on and on. And 20 kilowatt hours a day is about a 5 kW array. And that's small stuff now. And you can get a pretty reliable calculation if you go to NREL-SAM, which, by the way, is free and is fun and it's very intuitive. So if you want to see what a solar system might do, download yourself a copy of NREL-SAM. The National Renewable Energy Labs will ask you for your email address so they can report that the person at this email address downloaded a copy of SAM, therefore it was worthwhile for you to fund the research that's gone in to coming up with this program. Just that simple. It's one of my favorite. Well, whenever I don't like what everybody else is watching on TV, I come into my computer and I do a pretend house and do a SAM analysis. So in any case, so if we want to make 20 kilowatt hours a day, then it might be a good idea to store 20 kilowatt hours a day as well. So maybe we can find a storage unit that has 20 kilowatt hours of usable storage. Okay, so we have to look around, and there's lots of them. So I'm not even going to try to think. The typical 20 kilowatt, your typical Powerwall is going to give you 13 and a half. Enphase has 10 kW or kilowatt hour units. Others, there's a whole lot of others in the energy storage, residential and commercial business these days. And then there's the large energy storage systems as well as these. There's your pumped hydro. That's big time stuff. And they've been around longer than anything else. Guess what this is? Anybody want to make a guess? Just go ahead and open up your mic and tell me what you think this is. 9, 8, 7, 6, 5. No, it is not a brewery. It is not a thing for making wine or beer. No, I gather that you give up on that one because I know you didn't forget where your raise hand button is. Oh, I know what happened. My participant. I didn't have my participant. Did anybody have their hand up? No. Okay. That's a big flywheel that will store a megawatt hours worth of energy. Here we have lithium storage, big batteries. Here we have liquid storage. And here we have a place out in the middle of the desert in South Australia that will store 100 megawatt hours, 129 megawatt hours of electricity, and it will deliver it at the rate of 100 megawatts. And it was built in less than 100 days. And here's how it works. It stores energy during the day or during the night, and it gives it back during the day when the grid needs it. Okay, forget about power outage and anything else, but there was a time when they lost a coal plant, and within less than a second, this thing came online and provided that 100 kilowatts of power to the grid. to stabilize the grid. So it's a fine way to stabilize the grid. Okay, pumping water uphill, you just saw a picture of that. Interesting to do the math, you know, foot pound is raising a pound 1 foot. Gallon of water weighs about 8 pounds. Figure out how many gallons you have to pump, how high per kilowatt hour, because we know kilowatt hour is 3,413 BTUs. You convert that to foot pounds. What a fun math exercise that is. Okay, the difference is that pumping water uphill used to be only by night. But now if you got excess PV during the day, you can pump water uphill during the day as well. So we get a little extra use out of these systems. There's your dominant storage, pumped hydro. Rapidly being challenged by other forms, by the way. Here's some more stuff that's coming. Check the time. Okay, flywheels. They're very good for regulating frequency. Capacitors. Very good for regulating voltage transients. Superconducting magnets, great for current transients. Where might you have current transients? Well, anywhere where you got chopped up current waveforms. So, and there are lots of those out there these days. High power batteries. Yeah, big high power batteries. Okay. Electric vehicles, we talked about that. Hydrogen. The only problem on hydrogen is it's kind of lower on efficiency to break that water into hydrogen and oxygen. And it takes the source of electricity to do that. Or one way or another, there is a possibility in the process of making hydrogen, you're going to dump some CO2 into the air. But folks seem to be a whole lot more optimistic now. They've been working on this problem for over 50 years. There now seems to be a fair amount of optimism that given renewable electricity for making hydrogen might be a fairly sensible thing for extending the range of automobile and other vehicle travel and moving into airplanes and other things. We know that hydrogen works just fine to get a space vehicle out into space. So all we have to do is harness that for some of the uses we got down here on the surface of the planet. And then there's weightlifting. You might want to Google this one. It's simply called lifting weight storage or weightlifting storage or weightlifting energy storage. Try Googling any of those. It basically, why lift water? Yeah, the density of water. Why not lift something that's more dense than water? Like mercury. Well, no, we're not going to lift mercury because mercury takes a fair amount of energy to produce. It's a little bit expensive, but folks in Europe are looking at other things other than concrete, which is very energy intensive, that are these particular materials are not so energy intensive. Like if you have a big chunk of stone, for example, one way or another. So keep your eyes open for weightlifting as something that it's actually commercial in a few spots right now. And then there's microgrids. In other words, if you can do it for your house, you can do it for your neighborhood with your own backup. So, you know, the zero energy building can also be a zero energy neighborhood, and they can be made on microgrids. And, you know, you can adopt your own objectives on microgrids. So what's going to happen to the grid if we do all this stuff? Well, here's what we've got. We mostly have generation, transmission, substations going to distribution, and all the electricity is going the same direction down to the loads. Not a whole lot of generation, except actually there is, because about 20% of all this stuff is renewable. And some measurable part now is beginning to come from some other places. So the future grid, if we all hang on for another 10, 15, 20 years, probably going to look a whole lot more like this. And it's very simple. There's going to be some baby-sized PV and some baby-sized storage in the neighborhoods. We're going to have, in some places, larger loads, like say a commercial neighborhood or industrial. But some of these folks are going to put small PV systems on their roof, and small is going to be bigger than baby, because baby is going to be less than 10 kW, and small is going to be more than 10 kW. And medium is going to be a little bigger, and bigger is going to be like those huge utility fields that are, say, 100 megawatts or bigger. And of course, that means big storage. And that big storage is out there now too. Huge storage operation going out near San Francisco. And there's a big storage, the second largest storage system in the United States right now is in Florida. So utilities are onto this. They realize if they're going to make electricity with solar, they need a nighttime source. So if you can build some storage relatively close to that electricity that's being dumped into the transmission system, why then you can justify having all that extra PV that only works during the day. So I call this the beginning of the story. It gives you some of the ideas what's out there, a few specifics on if you really want to do one or two of these things, how to do the math. And from here on out, let's see, do I have any more slides here? No, I don't. So, is there anything anybody wants to talk about? I'm going to open up my my participant box here. And since we have 7 people out there, if anybody wants to discuss any of this stuff, we've got some time. And then after all, this is a live class. So feel free to, if you want to type something into the Q&A, do that. If you have something to talk about, we've left about 15 minutes. What's the chat say now? If you try, the chat is usually left for communication with the oh, okay. Yeah, okay. That was a message from the host. There's Q&A. What do we got? Do I see fuel cells becoming simpler? You know what? If you talk to a fuel cell person, they'll tell you absolutely. And fuel cell is part of the hydrogen thing, of course. It's simply converting hydrogen directly back into electricity by a slower membrane operation. And I do, because there seem to be some breakthroughs coming through. I've seen a few messages. The problem with fuel cells up to this point has simply been round trip efficiency and their levelized cost of electricity. Folks seem to be coming up with some very interesting kinds of, I mean, I've got a PhD friend who has been following this, and he's enthusiastic. He thinks they're going somewhere. So I'm going to go with his thoughts on that and say, yes, I don't see it around the corner tomorrow, but I would guess within 10 or 15 years, we're going to see fuel cells maybe as a part of a large vehicles, like in a train, for example. Who knows? And the other part about fuel cells, possibly in industry, for industry use. Industry has a lot of reasons for having heat, and there may be some way to. Let's see, Donald, do you feel as if renewable might take a downward turn depending on the outcome of the coming November elections? Are you kidding me? Do you want to get political? You know what? Excuse me. It may take a slight downward turn, but we aren't the only guys on the planet, for one thing. And the Chinese are going like crazy, and the Europeans are going like crazy on the renewables. And India is going like crazy on renewables. That's a goodly fraction of the world population. We may lose some subsidies or whatever, but the IRA, the Inflation Reduction Act, has leveled off inflation pretty significantly, but also has put a lot of money into things like fuel cells. And what happens when that happens and people get interested in the stock market and the investors in the market get invested, then the politics kind of falls away from it because it's all about the dollar. And so I don't think it's going to take a nasty downturn, but it might take a slight downturn while people get adjusted. If I might end up revealing my political inclination here, I really shouldn't do that. So let's just say that if the party that would cause the downward turn ends up taking office, I guess I implied the party that's currently in has been in during the upward turn. But then again, the upward turn started in 1975. So long answer, but I think that's probably a fairly legitimate answer. I think we're going to be around for a long time. I think renewables are definitely here to stay. Okay, you've heard since LIDs are in variety and availability that while more efficient people are using more lights. Oh, I can tell you that happens, Timothy. Absolutely. People will tend to use more lights, so you don't get the factor of 10. And I'll tell you what else happens too. We did a study at the university I worked at back in 1984. And we just to see how much money you could save by putting in good air conditioners and good water heaters and stuff. And we did energy audits and analyzed how much energy we thought people could save. And we found they didn't save quite as much because instead of running their air conditioners at 80 degrees or 78 degrees, they were running them at 77 because now they could afford it. So yes, this happens. Absolutely, it happens. Your observation is 100% true. And yet the overall per capita use tends to be going down. Let's see, what's IEEE? IEEE 2800 2022. I'm not familiar with 2800 2022. This must be new. I've been watching IEEE 1547 2018. And I mean, that 1547 2018 opens it wide open for the utilities to get together and control inverters. I mean, why have a 100 megawatt PV field operating like crazy when the utilities come close to peak, the frequency is dropping, and the inverter, according to IEEE 1547, is supposed to shut down. You want to keep it on. You want it overriding. You want to have power factor control, all stuff like that. So I'd be very curious now that I've seen 2800. I need to research that because I've been watching 1547 and had thought that had been pretty much the guideline. They had another addendum in 2020. But thank you for mentioning that because if you have any more you want to say about it, feel free to open your mic because I'm sure not the only one. I'm sure that I'm not the only one who'd like to hear more.
Happy to do that. Can you hear me?
I can hear you just fine. Yes, please proceed.
So, starting with some of the wildfires in California, they noticed that inverters that with there's what would be routine disturbances on the bulk power system, trips and recloses, inverter-based resources were not returning quickly enough to catch the ball to keep the frequency up, like you were just saying. And so IEEE, group of people involved with the power business, started a process for implementing a new inverter-based resource coordination standard, interoperability of inverter-based resources. There have been a number of those events since the first one, and one in two of them in Texas in the Odessa region, where particularly the second one, the amount of lost PV almost exceeded the design contingency for the ERCOT system in Texas. And then there would have been, rotating blackouts, but it didn't come to pass. But it's spooked the regulators enough that they are now implementing processes to take advantage of what was being created as a result of that learning. Is this IEEE 2800? It's passed in 2022, and it sets the requirements for interoperability of inverter-based resources with utility traditional systems, control systems and protection systems. So the point is, it may slow down some inverter-based resource introduction until they figure out how to actually bring their equipment up to the standard that's being pushed. In New York, it's been adopted. In Quebec, it's been adopted. And other regions of the country are in the process of adopting it.
Yeah, no, okay, maybe this has to do with what I hadn't necessarily identified with IEEE 2800, but the idea that starting the grid back up after it goes down has traditionally been the job of rotational sources. And that takes a while for them all to get in sync. But you can synchronize electronic sources within less than a second. And so the talk has been, how about why don't we work toward restarting the grid with the electronic inverters with one master starter, and then everything else locks in on that. And it seems the experiments they've been doing have shown the grid can be started a whole lot faster this way than gradually bringing in all the rotating sources. Is this part of 2800?
They really did not get into grid forming as much as it's grid following, which is the majority of the installed base. But grid forming inverters do have the capability that you are talking about, but there just aren't any, no one's going into it because there's economics involved. It costs more to create a grid forming inverter. And the majority of equipment that's in the interconnection process in the various regions is grid following. So that is a future thing potentially. And it's unfortunate, but as usual, it'll take a blackout of some kind to bring everybody up to speed, just like in the aircraft industry. So, but that's a possibility, sure. Grid forming, grid flowing.
Of course, there are grid forming inverters out there. The Enphase IQ8 series are grid forming.
Yes, so, and I doubt we'll be doing grid forming to restart the system from the household.
Probably not, but the point is the technology is out there. So
the technology can be incorporated into utility scale when the time comes.
Yeah, absolutely. Herbert, are you by chance with the utilities? You've got a lot of knowledge that
well, 30 years with them and then another 20 years with regulators. So
oh, okay. Yeah, you're familiar with the scenario. Yeah, my background's academic, so I haven't been able to totally keep up with exactly what's going on, but
just go to the NERC website, NERC.com, and go to across the top. You'll see initiatives, and under initiatives, you'll see the IBR initiative. You'll find more than you can read.
Sounds good. Thank you. Anything else? I don't see any more. Oh no, that's your hand there. Okay, anyone else? If not, I guess I could have read some of those slides that I skipped through fast. On the other hand, for those who have an interest in them, they are available from the host. Do whatever you like with them. I happen to be the owner of them, and I think it's information that's worth maybe passing on to other people. I hope that at least somebody in the group today found that it was worth the spending the time and another step toward getting that renewal again. So I guess it's probably all right if we break a little bit early. Not that early anyway, and I appreciate the discussion. That was very, very interesting. Okay, well then, off to work, off to home, off to whatever. And thank you all for stopping in today. And what I see is that there's a fair amount of material here that is I've noticed just in the last couple of weeks that I hope to update. But I've been working on a book that I hope to get done first. And we'll see how we do on that. So Douglas, Timothy, and everybody else, I usually just leave my, I stay online till everybody's signed out. So as soon as everybody's signed out, I will sign out as well.